2.8 inverse functions. So first we're going to review the definition of a function before we start talking about an inverse function. So a function is a set of ordered pairs where every x value there is a unique y value. Graphically, use the vertical line test to determine if the graph is a function. So we've done this actually. This was back in 2.1. We talked about the vertical line test. And so in order to be a function, you had to pass this thing called vertical line test right here. So every x value only has one y value in return. But if you look at my middle graph here, that's not the case. If you look here, when x is, let's see, 1, 2, 3, 4. When x is 4, I'm getting two different values back in return. So this one's not a function. And then the third one, this one would be a function again. So that's kind of our basic definition of a function, is every x has a unique y value. Now, it's okay if you look in my first graph right here, if you look when x is 2, y is 1, and when x is negative 2, y was 1 also. And that was okay. That's okay, and that's still a function. Okay, so the first one's a function. But in order to have an inverse function, you actually have to be a very special function. You have to be a one-to-one function. Okay, and that's what we're going to look at down below here. And one-to-one would mean that for every x, one y, and for every y, one x. And so this graph right here would not actually qualify as a one-to-one function. And then obviously the middle one's not one-to-one because it's not even a function to begin with. And then the third one, this one actually would qualify as a one-to-one function. So we're going to look a little bit closer at that down here. So right here, one-to-one function, a function is said to be one-to-one if each y value corresponds to only one x value 2. Graphically, use the horizontal line test to determine if the following functions are one-to-one. So it's given that these are all functions right here, and they are. All three of these are functions. But the first one, and I already pointed this out with the one up above, does not fall into the one-to-one category because here I have y values that have two different x values, and so that's no good. It is a function, it's just not a one-to-one function. If you look at the middle graph seems fine. The middle graph is okay. That one is considered a one-to-one function. So each x only comes up once and each y only comes up once. And then same thing with my third function right here. So there's no duplicates of any of your y values. Here we have duplicates of y values that show up. Now, I will tell you as we move forward, there are ways of manipulating this to where you can actually use this and find the inverse function, but what you have to do is you have to limit your parameters. So what I could do is just basically kind of delete half of this and just deal with only positive x values. And then this all of a sudden would become a one-to-one function. And then I could possibly maybe try to find the inverse of this function. Okay, so you might be thinking, okay, well, what is an inverse function, right? Well, we're going to start pretty basic and talk about maybe inverse operations first. And so let me get a clean page here for a second. And so just real basic, inverse basically means opposite. And so if you add 5, the inverse of adding 5 would be to subtract 5, right? And then if you were to multiply by 5, the inverse would be to divide by 5. So those are inverse operations of each other. If you were to take something and square it, the inverse of squaring would be to square root, right? Or if you want to take something and cube it, the inverse would be to cube root that value. So those are inverse operations. And so functions, it's going to be very similar. You're just going to basically undo what was occurring in the original function. So let's go down here and look at this now. So what is an inverse function? All right, so only one-to-one functions have inverse functions. A function and its inverse can be described as the do and the undo functions. A function takes a starting value, performs some operations to this value, and creates an output answer. The inverse of this function takes that output answer, performs some operations on it, and we will arrive back at the original function starting value. And so I have some basic examples right here. So f of x, your function is x plus 5. And then the inverse, and by the way, we use this little, it looks like a -1 as an exponent, but it's not an exponent. This is actually function notation that just means the f inverse of x, the f inverse of x. So right here, I even have a little note. So the notation is the inverse of f. We just pronounce it f inverse of x. The -1 is not an exponent, okay? So it's not an exponent. This is a notation issue here. And so the original function was x plus 5. The inverse would be x minus 5. So for example, for part A, if you were to do f of, let's say, 7, okay, well, that would be 7 plus 5. That takes us to 12. That's my output, right? That's my output. Now I'm going to take the f inverse function and take that output and plug it in. So then I'm going to have 12 minus 5, and that takes me right back to where I was, 7. That was my starting point. So I started at 7, plugged it in, got 12. Then I took 12, plugged that into the inverse, and it basically, it had undone what the original function had done. So the original function added 5, the inverse function removed that 5, and I went right back to where I was. And my second example B right here would be basically the same. So I plug in whatever I want, I'm going to double it. Then if I plug it into the inverse, I'm going to cut it in half. And so I'll just go right back to where I was. And I've got a little bit more of this on the next page to kind of illustrate this. So right here it says the graph of f inverse is a reflection across the graph of f. The reflection of the graph of f across the line y equals x. An inverse function maps the output values of a function back to the input values of the original function. So I just did an example of that on the previous page. The table of an inverse function has the x and y values interchanged from the original function. And so I left this little area over here so I could kind of show you this. So if we take this right here, here's the original function of this example I have. And so we're going to have our x values, and then for my y values, I'm just going to call them f of x so I can distinguish between the original function and then the inverse function. So for example, let's just plug in some simple values. Like if I were to let x equal 0 right here, 0 times 2 is 0, take away 3, so that'd be -3. Let's plug in 1. If I plug in 1, 1 times 2 is 2, 2 take away 3 is -1. If I were to plug in a 2, 2 times 2 is 4, minus 3 is +1. And I'll do one more. Let's plug in 3. 3 times 2 is 6, 6 take away 3 is 3. Okay, so I'm going to go ahead and plot those points so we can see them on this line. So we have 0, -3. We have 1, -1. 2, 1. And then right here at 3, 3. Okay, and so the definition up above is saying that the inverse of this green line will reflect across the line y equals x, which is this dashed line right here. So see all these red points right here reflect across and land here. Let's see, and this was at 1, -1, so it'll be -1, up 1. And so what's happening here is the x and y values are just getting interchanged. And so if you just switch the order of them, so you'll see when I create a table for the inverse function. So f inverse. So for example, if I plug in -3 for x, you can see that when x is, you can plug it into the equation if you want. But if you look on the graph, when x is -3, y is 0. When x is -1, y is +1. When x is +1, y is 2. And then here that point is on the line of reflection, so they share that common point right there. And so the point of this exercise I want to point out is that they switch, you just switch them, the x and y values. So 0, -3 is now -3 and 0 and so on for all the points. And so what's going on here is you kind of have like a loop going on here. And so I have this example here. So let's do this one real quick. Because if I plug in, let's see, if I plug in 5, let's see, 5 times 2 is 10. 10 take away 3, it's 7, right? And then if I take that and I plug this in here, I plug in 7. 7 plus 3 is 10. 10 divided by 2 will take me back to 5, okay? So we kind of have that loop going on here. And so here's kind of a visual of this. So I take the 5, I plug it into the f function, and it gives me a 7. I take the 7, I plug that into the inverse function, it takes me right back to the 5. And so that that doesn't quite prove that they're inverses. What I have to do is prove what's above here. And so instead of plugging in 5, I have to plug in x. So I plug in x and it gives me something in return. It actually won't be exactly y, it'll be something else, right? And whatever it gives me, then I'm going to take that and I'm going to plug it into the inverse function, and it needs to map me back to the x value. And if that happens, then that proves that the two functions are inverses of each other. And so technically you really need to prove it in both directions. You want to go from here to here back. And then also sometimes you want to start here and plug this into the inverse and then see if the original function will also map me back to my starting point. And that's what we're going to look at down below. So here's a more formal definition. So if f is a one-to-one function, then the f inverse is the inverse if, so what we're going to do here, we should be familiar with this notation from our last section. We're going to plug x into the inverse function, which then will just basically give us the inverse function, whatever it's defined as. Then we're going to stuff that into the f function and see if that returns an x, okay? And then we're going to do the same thing, but in reverse. We're going to put the x into the f of x function, which will give us that function, plug it into the inverse function, and that should lead us back to x also. So really both of these need to be true, but if it's true for one, most of the time it's going to be true for both. There's very rare cases where it does not work in both directions, but sometimes you do want to be a little careful about that. So using that, we're gonna verify if these two functions, f of x and g of x, are inverses of each other. And so kind of like the definition up above, we're going to stuff the g of x function into the f of x function, and hopefully we get an x back in return. And then same thing here, we'll take f of x, stuff that into the g function, and see what happens there. So looking at this first example, example A, so we want to do f of g of x. And so if you're kind of looking at the picture that we did up above, you have this pool right here, right? So this is my x. I'm plugging in x. I'm going to plug it into the f function. Oh, I'm sorry. In this case, I'm plugging it into the g function to get started. We're going to plug it into the g function, and that's going to give me this in return. So I plug in x, and I'm going to get x minus 8 over 3. And so that's what I get. So I plug in x, and this is what I get, right? And so since it's not, a number like 3 or 4 or 5, I just have to leave it as x. And so now I have f of x minus 8 divided by 3. So that's where I'm at now. Now I'm going to take this and plug it into the f function, and my hope is that it will lead me back to where I started, which was x, because that was the first thing I plugged in was x. I plugged x into the g function. It gave me this expression. Now I take this expression, plug it into the f function, and let's see what happens here. So I'm going to get 3 times x minus 8 divided by 3, and then a plus 8. So I'm just plugging it in right there to that f function. And let's see, what's going to happen here is the times 3 divided by 3 actually cancel each other out. So then I'm left with x minus 8 plus 8. And then the minus 8 plus 8 cancel out, and I'm just left with x. And so yes, they are functions. So thus, and this is how it will look on your homework, thus f and g are inverses of each other. Okay, f and g are inverses of each other. Now technically I should check it the other way, and I will, just so we can get that extra practice. But like I said, we shouldn't really run into any of those cases where it works one way and not the other way, but it is possible. It is possible that it can work one direction but not the other direction. But like I said, those are pretty rare and they're not going to be something we're going to deal with in college algebra. But just to, like I said, to get a little extra practice, now we'll do it the other way just to be extra careful. So we take the f of the x, plug it into f of x, and we get 3x plus 8. So now we're going to have g of 3x plus 8. Now we take that, and we're going to stuff it into the g function right there for x. So that's going to be 3x plus 8, and then minus 8 divided by 3. So that's the other parts of the g function, right? So I plugged in my x, and I have this other stuff going on here. Well, the plus 8 minus 8 will cancel out, so then I'm left with 3x over 3, which then the 3's will cancel, and I'm just left with an x right there. So yes, I showed that we have that kind of loop going on there. So I started with x, applied some operations to it, got this, then applied some more operations, and I got right back to where I started. And so basically I established that there's that loop going on there between the two functions. And so this is how you prove that they are inverses of each other. Also, this won't always be the case, but on some of these easier ones, it is kind of obvious when they are, because if you look here, on one of them, you're multiplying by 3, and then you're dividing by 3. You're adding 8, you're subtracting 8. So sometimes it can kind of be obvious that they are inverses of each other, but they can get more complicated to where you're not going to be able to tell just by looking. You have to do this process. Okay, let's look at example B. So, give myself a little bit more room. So we're going to do the same thing here. So we'll start with doing f of g of x. And so we're substituting x into the g function and we get this. So then that's what g of x is. So f of x plus 5 over 9. And then now we're going to plug that into the f function right there. So now we've got 5 times x plus 5 over 9, and then take away, I'm sorry, yes. So x plus 5 over 9, and then take away 9. Okay, if it's going to simplify into x, so we're kind of wondering, that's what you're trying to figure out. Is it going to equal x? If it's going to happen, it usually happens pretty easily. And if you saw on our work over here, the 3's canceled out, the 8's canceled out, and so on, and we had a similar thing that happened on my second part, the g of f of x. It happened pretty easily, right? Well, here, the 5 and the 9 are not going to cancel. So you can kind of play around with this, but it's not going to work. So this is not going to simplify and equal x. So what does that mean? That means that f and g are not inverses. So if are inverse functions, they are not inverse functions. So if it doesn't work for one, you can just stop. Now, if it works for one, technically you should go ahead and test it for the other way of doing it, stuffing it the opposite way. But if it doesn't work for one, right there, you can just stop. And so, like I said, it should be pretty obvious. Now, moving forward, what we're going to do in the second part of the video is we're going to be just given a function and you're going to be asked to find the inverse. And so this is good testing it, trying to figure out if two functions are inverses of each other. But what's going to be better is actually being given a function and asked to find the inverse function. So that's what we'll do in part 2.